Hey guys, this is the last of the 9 common techniques for rewriting integrands. I scratched that out. It's actually evaluating integrals this time. This is not about using algebra or using trigonometry to rewrite the integrand. This is about evaluating definite integrals of functions over what we're calling even intervals. But in order to get there, we need some definitions. So we're going to start by talking about even and odd functions. You probably learned this in college algebra or pre-calculus 1. We say that a function is even if f of x and f of negative x are exactly the same for all x, or for all x in the domain. Now you might say, well, what does that mean, really? This is saying that if I go x units in one direction, and I go x units in the opposite direction, and I find those two y values are going to be the same. So here's an example, a very simple example of an even function is f of x equals x squared. When x equals 0, y equals 0. 0 squared is 0. When x equals 1, 1 squared is 1. Negative 1 squared is negative 1 times negative 1, so that's also positive 1. So this is at x equals 1. When x equals 2, y equals 2 squared. So we get 4, or negative 2 squared. Negative 2 times negative 2 is also positive 4. And so we've got something that looks like this. Alright, so there's a y and there's an x. So that's an even function. You might be saying, okay, what was that again? What was that about this f of x and f of negative x? Okay, here's the key quality of an even function. If I go x units in this direction and I find the y value, and I go x units in this direction and I find the y value, those two y values are the same. Maybe not on my graph, it's not quite to scale. Maybe I didn't draw a perfect picture. But that's the idea. X units to the left, x units to the right. The y values are the same. So f of x equals x squared is an even function. We could check that algebraically by replacing x with negative x. So negative x squared, remember that's negative x times negative x. A negative times a negative is a positive, so that's the same as positive x times positive x, or x squared. And that's the same as f of x. So I've just shown that f of negative x turns out to be exactly the same as f of x. After simplifying, I get exactly the same thing. So if f of negative x and f of x happen to be the same thing, then we say that this function is even. Another familiar function that's even is the cosine function from trigonometry. Remember how cosine looks? It starts at its max, its maximum value of positive 1. And then at pi over 2, it's at 0. And at pi, it's at its min of negative 1. Then at 3 pi over 2, it's back to 0. And then at 2 pi, it's back to positive 1. So it does this. And it continues forever in both directions. I'm going to try to draw my graph as symmetrically as possible so it's a little bit easier to see these properties. Still sometimes hard to draw. Alright, but this is our cosine function. This is what it looks like. Notice what happens. If I go x units in this direction to say pi over 4 and I find the y value, and x units in this direction to negative pi over 4 and I find the y value, I get exactly the same value. The y's are the same. Or if I go to x equals pi and I find the y value, I get a y value of negative 1. If I go to x equals negative pi and find the y value, I get a y value of negative 1. So cosine of x and cosine of negative x, those two y values are the same thing for all x in the domain of cosine, which happens to be all real numbers. So cosine is an even function. Now you also want to remember that according to the fundamental theorem of calculus, actually, it's not the fundamental theorem of calculus. The fundamental theorem of calculus says if I have the integral from a to b of f of x dx, first I take the antiderivative, then I plug in the upper limit and I plug in the lower limit and I subtract. So one way that I can write that is f of b minus f of a. And we're right there with the fundamental theorem. Now, this is not exactly related to the fundamental theorem, but it is related to how we interpret it. If f of x is a positive function, let's say it's greater than or equal to 0 on the interval from a to b, then this integral from a to b of f of x dx represents the area, what we call the area under the curve. And what we mean by that is that when we look at the graph of f of x, if it's positive, maybe it's doing something like this. And here's x equals a, and here's x equals b. When I evaluate that integral, I'm going to get a number. I'm going to use the fundamental theorem of calculus, take the antiderivative, plug in b, plug in a, and subtract. And I'm going to get a number. That number is that area right there, if this is y equals f of x. And this is x equals a and x equals b. Now, if the function happens to be negative sometimes, so f could be positive sometimes and negative sometimes, we say that the integral from a to b of f of x dx represents net area. And this is something like the area of the function, or area between the function and the x-axis on the interval from a to b. So maybe your function looks like this. Maybe this is x equals a, and this is x equals b. Well, there's area below the x-axis at some points, because my function is negative over there, and then at some point it goes from negative to 0 to positive, and it switches. And I get this area over here. If I call this area 2, and I call this area 1, the integral from a to b of f of x dx represents the area above the x-axis, so that's going to be area 2, minus the area below the x-axis, that's area 1. Now, I still believe, I hold the convention that area is always positive. It's a measure of some number of square units, and you're not going to have any negative numbers of square units. But that does not mean an integral can't be negative. A definite integral could very well be a negative number if this area below the x-axis is greater than the area above the x-axis. So this is representing some kind of net area or area under the curve. And so we want to keep all of this in mind and keep the fundamental theorem of calculus in mind as we talk about areas under even and odd functions. So now let's imagine that you're on an interval not from a to b, but from negative a to a. So maybe our interval is from negative pi over 2 to pi over 2 for this cosine function. You guys see that there's some symmetry? Do you see that the area on this side is going to be equal to the area on this side? And what if I changed my a values? Instead of going from negative pi over 2 to pi over 2, what if I went from negative pi to positive pi? Well, that area and that area are the same. So I could just take that area and double it. And that area are the same. So I could take that area and double it. So I could do that one minus that one and then double it. Or I could do that one minus that one and then double it. The same thing happens up here with f of x equals x squared. If I look at this, whatever that x value is, in this area, because it's even, because I'm going from negative a to a, the area on this side between 0 and that a value is equal to the area on this side between 0 and the negative a value. So if my function happens to be an even function, and we are evaluating a definite integral on what's called an even interval, and we're using even in 2 different ways, I'm so sorry. But if we are evaluating the integral, from negative a to a of f of x dx, and f is even, we're just going to get 2 times the integral from 0 to a of f of x dx. You might say, that doesn't really do much for me. I still have to take the antiderivative. I have to plug in a and 0 and subtract. It is still a little bit of work, but often the algebra and the arithmetic is a little bit easier and cleaner if you're not having to worry about the negative signs that you would worry about over here. So it's a nice property that we take advantage of occasionally when we can see, when it's very clear and obvious that the integrand is an even function. So this is true when f is even. And if I want to use this fact to evaluate an integral, I need to show that the function is even, and we're going to show it algebraically by showing that f of negative x and f of x, the y value to the left and the y value to the right, I did that wrong, left and then right, no, I was right the first time, left and then right, show that those y values are exactly the same thing. If we do that, then instead of evaluating this integral, we can evaluate that integral. One other thing that you should know about even functions, even polynomial functions are easy to spot. A polynomial function is even if all of the terms of the given polynomial have an even degree. Doesn't mean the whole polynomial has to have an even degree, although it does. But what we're saying is every single term of that polynomial has an even degree. And it can also have a constant term because a constant is multiplied by an x to the 0, and 0 is an even number. So here are some that are even. F of x equals x squared is even. We know geometrically it looks like that. It's even. X units this way and x units this way, the y values are the same. Of course, f of x equals x to the 4th is also even. It's actually just a little bit flatter. I think I did kind of a poor job of showing it. It's actually a little bit flatter between -1 and 1, but it has basically the same shape as x squared. Let's see something like this. Maybe it's got an x to the 4th minus let's say 4x squared. So if I factor out an x squared, I've got that. Oops. That is an even function. You might say, how on earth would I know what that looks like? It's okay if you don't remember. Did this a little bit in college algebra, also known as pre-calculus. This function is 0 when x is 0, it's 0 when x is negative 2, it's 0 when x is 2. Yeah, there you go. And then at x equals 1, we're going to have 1 minus 4, so that's negative 3. At x equals negative 1, we're going to get the same thing because negative 1 to the 4th and negative 1 squared are the same as positive 1 to the 4th and positive 1 squared, so we're going to get negative 3. And I believe it looks like this. Sort of a W shape. You don't have to know what this looks like in order to tell that it's an even function. I see the x to the 4th and the x squared. I know it's even. If I added a 5 to that, it would still be even because the entire graph would just be shifted up 5 units. Also, the 5 would just have an x to the 0 attached. So we've got an implied x to the 0. If all those exponents are even, it's an even function. So for all of these, for every single one of these, if I wanted to, let's say the integral from negative 3 to 3 of x squared, I could just use the power rule, plug in negative 3 and 3 and subtract. Or I can use this fact. Well, that's the same as this. Double it and just integrate from 0 to 3. So if I integrate from 0 to 3, or first I'll anti-differentiate, get that. Plug in 0 and 3 and subtract. Here we go. 3 goes into 27 9 times. And so we get 18. And that's the area under the curve. So that's one simple example of that. But that's a property that we can take advantage of for even functions. And even polynomials are easy to spot. Also, you should know that since we also mentioned earlier that cosine of x is an even function, so cosine of negative x and cosine of x are the same for all x. All x in the domain of cosine, which is all real numbers. If I take this even function and I multiply it by an even function, it's still even. So f of x equals x squared times cosine of x is even. F of x equals x to the 4th minus 4x squared times cosine of x, still even. Even if I multiply it by something that doesn't look even, like a 7. 7, that's 7 times x to the 0. That's an even function times an even function, so this is even. Here's another even function. I have no idea what this looks like. And I see that 7 and that 3 and that 1, and I'm thinking it's probably not even, but that doesn't matter. We've got an x to the 10th, x to the 6th, x to the 4th, and then there's an implied x to the 0, 0, 4, 6, 10. All of those are even. So if I replace x with negative x, I've got 10 negatives multiplying each other. All of those are going to cancel. They cancel in pairs. And I've got 6 negatives multiplying each other. because the because the negatives cancel in pairs, x to the 10th is equal to x to the negative 10th. X to the 6th is equal to negative x to the 6th, and so on. So this is even though it might not look like that it's even. So keep that in mind. If you have an even function times an even function, the result is going to be even. All right. The second type of function is the one that we use most often, or more often, with this symmetry property. And this is regarding odd functions. An example of an odd function is f of x equals x cubed. All right. So here is a graph of positive x cubed. 0 cubed is 0, 1 cubed is 1, 2 cubed is 8. Negative 1 cubed is negative 1 times negative 1 times negative 1. That's negative 1. Negative 2 cubed, negative times a negative is a negative 8. So that is my cubic function. So here's the property. All odd functions, and this one is just one particular example, have this property. If you go x units in this direction and you find the y value, so that's f of x, and you go x units in this direction and you find the y value, that's f of negative x. They're not the same, but they're opposites of each other. If I go 1 unit this way, I get a 1. If I go 1 unit this way, I get a negative 1. If I go 2 units this way, I get an 8. If I go 2 units this way, I get a negative 8. So the y values, that's f of x and f of negative x, are opposites. So sometimes we'll write it this way. Negative f of x is equal to f of negative x for all x in the domain. Or you could just multiply both sides of this equation, by negative 1, and you get this. But I'm just saying this y value and this y value are opposites of each other. All right, so that's an odd function. Another example of an odd function is sine of x. And I think I'm going to use another sheet of paper for sine of x. One of my favorite professors from TCC, Larry Starhill, used to say you should never date a person who can't draw a pretty sine function. I don't know what to think of that advice, but I thought it was cute. Want to draw a pretty sine function. So with sine, you're going to start at 0, and then at 1/4 of the period later, at pi over 2, you're going to end up at the maximum of 1. Then 1/4 of the period later, you end up back at pi. And 1/4 of the period after that, that's 3 pi over 2, you're at negative 1. And then you get back to 2 pi. So you got 0, 1, 0, negative 1, 0, and so on. And you keep going. And you go forwards and backwards. So this is negative 2 pi, and that's negative pi. It's negative pi over 2 and negative 3 pi over 2. And the pattern continues. So we have a negative 1, a 0, a positive 1, and a 0. That's our sine function. continues on forever in both directions, repeating that pattern for all time, for all x. It's quite beautiful. Now this is an odd function. If I go pi over 4 units this way, find the y value, I get square root of 2 over 2. If I go pi over 4 units this way and find the y value, I get negative square root of 2 over 2. So in general, sine of x and sine of negative x, they're not the same, but they're opposites of each other. Now, it's not factoring. It's absolutely not factoring. You can never take something out of the angle and pull it outside. Like there's a 3x, you can't call that a 3 times sine of x. You're not factoring it out. But it kind of looks like factoring whenever you're using this property of odd functions. Sine of negative x is the same as negative sine of positive x. And that's true for all x. Can you imagine what's going to happen when I evaluate the integral of this over an even interval? So we'll say if f is even, or excuse me, if f is odd, the integral from negative a to a of f of x, well, it's this area minus that area. But because of symmetry, aren't those areas exactly the same? If this area and this area are exactly the same, I'm just subtracting two areas that are the same. It's this minus this, and so I get 0. What if I went to pi over 2? Same thing, isn't it? It's going to be this minus this, and I'll get 0. Or 3 pi over 4. Taking that area, I'm subtracting that area, and I get 0. So it turns out, and I haven't proven it, but it turns out that if I evaluate this integral from negative a to a of f of x, and f is an odd function, I just get 0. If I want to use this fact, I have to prove that f is odd. So as you're doing your homework, as you're practicing, you make sure that you show or can show that f is odd. And showing algebraically that f is odd means that you're showing that f of x and f of negative x are opposites of each other. Okay. Before we get into an exercise or a practice problem, let's talk about other odd functions. Polynomials with odd, I'm going to say odd degreed terms, are odd functions. So f of x equals x to the 5th minus 2x cubed plus x. That's odd, because that's a 1, that's a 3, and that's a 5. Or f of x minus 100 x to the 15th plus 7 x to the 5th minus 6x cubed. That's also odd, because 15, 5, and 3 are odd. Not worried about the coefficients at all. What about this one? Even or odd, or neither? Well, that's odd, that's odd, that's odd. Careful here. That constant is not odd. It's not an odd degreed term. The degree of that term is 0, and 0 is an even number, so this is neither even nor odd. And another thing that you should be aware of is that if I take an odd function and I multiply it by an odd function, the resulting function is even. And I think that makes sense, because let's say let's say that we assume that f is odd and g is odd. And I'm considering this new function f of x times g of x. Remember back in algebra we called that f times g of x. It's defined to be the original f of x times the original g of x for all x in the overlap of their two domains, but we're not going to get too much into the domains right now. So let's assume these guys are odd, both of them are odd, and then we write it like this. Well, remember, if f is an odd function, I can replace that with negative f of negative x, because f of x and f of negative x are opposites of each other. And if g is odd, well, then I can replace g with negative g of negative x. So this is a negative times a negative. So it's a positive, so I have f of negative x times g of negative x. And that's going to be f times g of negative x. And so what I've shown is that f times g of x and f times g of negative x are exactly the same thing. The only way that happens is if f and g, or f times g, is even. Okay. If you're having trouble with that logic, don't worry about it. That's just a proof of this fact. You can just memorize the fact if you prefer. Or you can roll it back and think about what I just said. Remember, a function is even if the function evaluated at x is equal to the function evaluated at negative x. And that's exactly what happens here. If f and g are odd, we get the product evaluated at x is equal to the product evaluated at negative x, so the product has to be even. So we have an odd times an odd is even, and an even times an even is even. We said that on the last page. And it turns out that an even times an odd is odd. And that's because one of these guys is going to have a negative and the other one's not. So it's going to have like a negative out front. You can prove that yourself though if you want to. So keep those properties in mind as you are evaluating the definite integrals in this section. So here's an example. Let's say somebody asks you to evaluate the integral from negative pi to pi, or excuse me, negative 2 pi to 2 pi of x cubed times cosine of x. Now, with the techniques that we have learned so far, we don't actually know how to take the antiderivative of this. We're going to learn how to take the antiderivative of this in the next section with a technique that's called integration by parts. But with the techniques we've studied so far, we actually can't write down the antiderivative of this. So I'm hoping, since it's an integral from negative a to a, I'm hoping that that is an odd function, because that's the only way I'm going to be able to evaluate this. And if it is odd, the area under the curve from negative 2 pi to 2 pi, the net area, the area above the x-axis minus the area below, is going to be 0. So I'm saying f of x is equal to this. And in order to prove that this integral is 0, I need to show that this function is odd. So I need to replace x with negative x. And then simplify. So this is a negative times a negative times a negative. And I've got cosine of negative x there. The negatives cancel in pairs. So we end up with a negative x times x times x, which is negative x cubed. And cosine of x is cosine of negative x is cosine of x, because cosine is an even function. So we end up with that. Is that f of x? No, but it's the opposite of f of x. And that's exactly what we want. The y value at x and the y value at negative x, they're not the same, but they're opposites of each other. So that means that f is odd, and if f is odd, the integral from negative a to a of f is 0. You can also have proved this by saying that x cubed cosine of x is odd because y equals x cubed is odd and y equals cosine of x is even. And we know that an odd function times an even function is an odd function. So that's another way to prove the same thing, just using a known fact that we've stated up here and put in boxes. So keep those two facts in mind as you are evaluating the integrals in this section. If f is odd, and you got to be able to prove it, the integral from negative a to a of f of x dx is 0, because that area minus that area is going to be 0. Those are the same area. Now, if f is even, you've actually got a little bit more work to do. If I look at the area to the left of 0 and the area to the right of 0, they're going to be exactly the same. So it's actually that area doubled the area to the left, or that area, that net area, doubled. So here is our theorem, or our fact, for even functions. Here it is at the top. If our function f is even, then the integral from negative a to a of f of x dx is twice the integral from 0 to a of f of x dx.